So today I'm going to talk about reftable like I typically tend to do at any kind of conference. So I'll cover what reftable are, where we're going with reftable, and also why you should actually care about reftable in the first place. So first, I want to introduce myself. Like I was already introduced, my name is Patrick Steinhardt, also known as Steiny the reftable guy by now somehow. I don't really know how that name actually came to be, but that's it. So I started diving into Linux in 2002 when I was like 11 years old, became an open source contributor in 2011, and nowadays I'm a Git and libgit2 contributor since 2015, backend engineer at GitLab since 2020, and manager of the Git team at GitLab since 2024. But that's enough about myself, so let's talk about reftables. First, I need to explain a little bit what reftables actually are. This is not really anything new for a bunch of folks in this room, but it doesn't really make a lot of sense to talk about reftables if you don't really have the context what they actually are in the first place. Before talking about reftables, though, let's talk a little bit about how Git stores references in your Git repository in the past. When creating or updating references, they're by default stored in the so-called loose format. Every reference is stored as a separate file. The reference format is actually quite straightforward and also very easy to grasp. So to demonstrate, let's create a simple repository with a commit and a branch. The first file we'll examine is the head file. This reference indicates the currently checked out commit in your repository. As you can see, it has a refs column prefix, which basically indicates that this is a symbolic reference where the target is refs heads main. So we know that we have the main branch checked out in this repository. All the other references are stored on the refs directory hierarchy. As we can see, we got two files in there in refs heads, which is feature and main, and these are our branches. And also, as you can see, these have the object ID they are pointing to as contents. Now, storing every single reference as a separate file only works well when you have a handful of references in your repository. But when you have hundreds or even thousands of references, then it becomes really inefficient. Every single reference needs a separate inode, which on many file systems means it has to store it on a full disk sector. And also listing all of your references becomes increasingly expensive as you have to go through all of those files and to open all of them. So to counteract this, Git regularly packs your references into the packed refs file. You can manually pack your references by executing git pack refs --all. Git usually does this automatically for you as part of Git maintenance, which gets executed after several other commands, like for example git commit. As you can see before and after executing git packed refs --all, now all of our loose references have actually vanished. Instead, we now got a git packed refs file, which is simply a sorted list of all of the references that have just been packed. Reftables are an alternative backend for storing references in your repository. So let's again create a repository, but this time around with the reftable backend by saying --ref format equals reftable. First, we'll have a look at head. As you can see, it still looks like a symbolic reference, but it actually points to refs heads.invalid. This file really exists as a compatibility shim, because Git does not consider a repository unless it has a head file. The second step we have in this repository is git refs head. Previously, this has been a directory, but now it's actually a file that contains some garbage. So if Git clients actually want to access that repository with the files backend, then they would be expected to fail, which is kind of a safety mechanism. The git config file also looks a little bit different compared to a normal repository. Most notably, at the bottom it has this extension which is saying ref storage equals reftable, which is basically what tells you that this repository is using the reftable format. The first data structure that is actually specific to reftables is the tables.list file. This file tracks the currently active list of tables. So whenever you update a reference, Git will write a new reftable to the repository and append it to this specific list. This mechanism is really important to reftables because it allows for atomic updates. You can get a consistent snapshot of all the references in your repository by reading the tables.list file and then reading and loading all of the reference tables. And you can perform an atomic update in the repository for multiple references by writing a new table, writing a temporary tables.list file, and then atomically renaming the temporary file into place. The tables themselves are stored in a binary format. While the binary format is way more complex compared to the old files backend, it also allows us to store data more efficiently. We won't dive into all of the intricate details for how this format actually looks like, but there's still a couple of things that you can actually see here. First, we've got a reft prefix, which indicates that this file is a ref table, and it also indicates the header of the file. There also seems to be something like a footer, because you can see that there's a second reft string in this file. You can also see our head reference, which seems to be a symbolic reference pointing to ref's head's main. As I've mentioned already, Git will append a new table to your tables.list file every time you update the reference. So when we create a new commit, you can see that our tables.list file now has actually two entries, the old table that we already had and a second one. So let us again have a look at the contents of that file. And we can again see some interesting things. We've got the ref header and the footer again. We've got the ref's head's main reference, which is what we just updated. And that reference is followed by the object ID of the newly written commit. Note that in this case, the object ID is actually not stored in hex, but it's directly stored in binary, which is more efficient to store on your hard disk drive. Of course, we cannot just keep on appending new tables to the stack whenever we write a reference, because that would quickly get out of hand if we had hundreds or thousands of tables. To prevent the list from growing too long, we use auto-compaction. Whenever we append a new table or a new entry to the list, we check whether some of the tables should basically be merged together. So let's create another branch. As you can see, this time around we didn't actually append a new table. Instead, we end up with a single merge table that contains all of the references of that repository. You may have noticed that each of these tables actually has two increasing counters. These counters encode the minimum and the maximum update index of records contained in that specific table. Before our auto-compaction, this first and second update index were always the same for each of the tables. But now that we have merged multiple tables into one, we can see that the first number is the minimum update index of contained records, whereas the second update index is the maximum contained update index of that specific merged table. The reftable backend uses geometric sequences as a heuristic to decide whether or not tables should be merged together. Each table must be at least twice as large as the next smaller table, and if that geometric sequence is violated, we'll merge as many tables together as required to restore that property. You can see it come into play quite nicely when I create a lot of branches, like for example in this case where we create 1,000 different branches, and there you can see with the file sizes that this geometric sequence is always honored. The reftable backend was merged in Git 245, so already more than a year ago. Naturally though, getting reftables merged was only a starting point, and there are still lots of things we had to do. So where are we going with reftables overall? The first obvious one is performance optimizations. The files backend had 20 years of performance optimizations, and initially for the reftables backend our focus was not to get it fast, but rather to get it correct, so that we don't lose any data, for example. So while the reftable backend should be faster in theory in lots of use cases, there are certain edge cases where it's not the case yet. One of those cases where the reftable backend should be significantly faster is when writing many references at once. Because in any case, we only have to write a single new table and then only append that to the tables.list file. So we only have to write two files to the repository. So with that knowledge, I was very surprised when this particular email arrived in my inbox. Brian claims that when deleting all references in a repository and then recreating them, then the reftable backend is significantly slower compared to the files backend. In fact, more than 50 times so. Now, we may agree that deleting 50,000 references only to recreate them might not be really the most typical use case in a repository, but it still very much left me puzzled why that actually is. As it turns out, this was quite an interesting edge case that he discovered. See, with the reftable backend, a deletion does not actually end up deleting the reference from the whole stack. Instead, you end up creating a new table that contains a tombstone that basically marks that reference for deletion. This is in contrast to the files backend. Whenever you delete a reference, it immediately gets deleted from the whole reference database and there's no trace of it left anymore. But with the reftable backend, we may only decide to merge the tables at a much later point in time, and it's only at that point in time where the reference will be truly gone from the whole stack. But why do we even care about that? The answer here is conflict checks. Whenever you update a reference, we need to verify that there are no references with conflicting names. So for every reference, we have to check whether there is a reference that has the same prefix, or whether the reference itself is a suffix to another reference. And if that is the case, then we have to abort the reference transaction. This is obviously cheap to check in a repository where there are no references, because all reference lookups will simply yield nothing immediately. But with the reftable backend, we first have to figure out whether every single reference actually has been deleted already with a tombstone, which is way more expensive. So how do we fix this? We batched the conflicts checks. Previously, we always performed the conflict checks for every single reference individually, which had the effect that we would check 50,000 times whether refs had sum exist, whether refs heads exist, and whether refs exists, which is overall quite a waste of time. But with the batch conflicts, we don't have to check refs heads again if we've already verified once that it doesn't exist. And this led to quite a significant speed up. Where previously it took around 80 seconds to create 10,000 references if they had been previously deleted, it now only takes 11 seconds. This is still not particularly great, to be honest, but it's definitely a significant improvement. Another area where the reftable backend is lacking is when performing many separate reference transactions or updates in separate transactions. For every single transaction, we not only have to write the new table and the tables.list file, but we also have to perform the auto-compaction to ensure that the list of tables is kept at bay. But there are a couple of use cases where we actually have to create multiple transactions, and the added auto-compaction is actually quite costly here. One such use case is fetches. Whenever you execute git fetch, we update each reference in a separate transaction. This is done so that if we fail to update one of the references, due to whatever reason, all the other updates might still actually succeed. Unfortunately though, reference transactions are atomic. We either update all references or we update none at all. So they're not really a good fit for this very specific use case. To fix this gap, we introduced batch transactions into Git. All reference updates are part of a single transaction, but we explicitly mark that transaction such that it knows to evict any unsuccessful updates from it, while continuing with the rest and committing the rest. After the fact, we can then figure out which of those references has been updated successfully and which one of those has failed. So we updated git fetch to use this new mechanism, which again leads to quite a significant speed up. Before, fetching 100,000 references took around 40 seconds. With the changes, it now takes only 1.5 seconds, which is a significant improvement. Furthermore, this mechanism has also been applied not only to git fetch, but also to git receive pack, which is what we use on the server side to receive pushes. And I very much expect that we will in the future also apply this optimization to other areas in Git. Another similar case is when you rename remotes. After rewriting the git config for the renamed remote, we also have to rename every single reference that belongs to that remote to have the new name instead. This operation is not even remotely atomic right now. If any of the rename fails, or if the user aborts, for example, the whole rename operation, then you're left with partially renamed references in Git right now. But besides being non-atomic, this is also painfully slow. When you rename a remote with 100,000 branches, it takes a lot of time. You can even watch every single branch getting updated one by one. So how long does it take? This particular example where we rename with 100,000 branches takes more than an hour. And actually, it ends up writing 186 gigabytes of data to your disk. I mean, the funny thing about it is, this is not even using the reftable backend. This is using the files backend. With the files backend, we basically have this packed ref file, which contains all the references. And every single time we delete a reference to rename it, we have to evict that reference from the packed ref file. With 100,000 branches, this file is 7 megabytes in data. And we have to basically rewrite that file 100,000 times, so that it ups quite fast. The reftable backend doesn't really perform particularly well in this specific case, but at least it doesn't have to rewrite all the references every single time because of geometric compaction. So how did we solve this? Again, we converted it to use a single transaction to batch all of the updates into one. We only have to rewrite the packed refs file a single time for the files backend, and we only have to write a single table for the reftable backend. So the performance graphs here are for the reftable backend. For 100,000 references, it previously took around 10 minutes, which is way faster compared to like over an hour with the files backend, but certainly not really what the user expects if they just want to rename a remote. After the change, it now only takes 12 seconds. This is only like an excerpt of different performance optimizations we did over the last couple of Git releases. And there's a lot of smaller optimizations that we did left and right. Overall, though, the trend is clear. We iterate a lot on performance for the reftable backend, and we'll continue to do so that it outperforms the files backend in all of those different use cases. So how do we perform nowadays against the files backend? Quite well overall. This is again only like an excerpt of benchmarks, of course, and real-world numbers might actually look quite significantly. But in most of the cases, you can see that the files backend is significantly slower compared to the reftable backend. Next to performance optimizations, we've also worked on tooling a little bit in Git. As reftables are a binary format, it becomes unfeasible to paper over gaps in Git tooling by just going to the file system directly, which is something that you could previously do with the files backend. One such use case that users had, though, was to basically list all the ref logs, for example, which are a log of all the operations you perform on a specific reference. It wasn't even possible to list all available ref logs in your repository without hitting the file system directly. So we introduced new tooling to list all available ref logs in a Git repository, to manually write a new ref log entry to one particular ref log, and to delete a ref log altogether, all of which didn't exist beforehand. In Git 246, we also introduced new tooling to migrate reference backends from files to reftable or vice versa, by introducing the git rest migrate command. One initial gap, though, was that you could not migrate repositories that contained ref logs, which is something that actually most repositories do. This limitation has then eventually been lifted in Git 249, so nowadays you can also migrate repositories like that. Also, if you want to be daring, you can nowadays tell Git to use the reftable format by default, as we introduced a new config variable init.defaultRef format. With this in place, every single time you create a repository by using git init or git clone, it will use the reftable format by default. So that leaves one more elephant in the room. What about the ecosystem? There isn't only one implementation of Git, but there's multiple different implementations. So who else is actually able to use reftables? For now, it's unfortunately only JGit, which is also where this format initially originated from. But just this month, we have finally finished implementing a fully working backend for reftables in libgit 2, where libgit 2 is a linkable library to access and write to Git repositories. One important user for libgit 2 is, for example, Cargo, which is Rust's official package manager. This work is still split up across 5 different pull requests, adding like 16,000 lines of code, none of which have been merged yet, but hopefully libgit 2 should have support for reftables sooner rather than later. The next one that I probably want to tackle is Gitoxide, which is a Rust implementation of Git. But for now, I have to be honest, I'm still constantly fighting with a borrow checker, so it will probably take a little bit of a while until I will finally get there. So with all of this, there's one more question. Why should you actually care about reftables? With the files backend, we were subject to a lot of specifics for the file system. Reference names are derived from the path names, which generates various different issues. You cannot, for example, have references that differ only in casing on case-insensitive file systems, like, for example, HFS Plus or NTFS. Also, some file systems like HFS Plus may decide to change the representation of Unicode characters in your path names. So the reference name you want to store on disk and the reference name that actually gets stored on disk might actually be different. And some file systems won't even allow you to create branches which are named something like com1, for example, because seemingly that seems to be precious memory to Windows folks. With reftables, all of these issues go away. While I very much hope that you don't have to work with a repository that has millions of references, such repositories do exist out there. And if you work on them, you might very well appreciate the improved performance that reftables actually brings to you. The files backend does not allow for atomic updates, as references are written one by one as separate files. This issue goes away with the reftable backend, where both reads and writes are fully consistent. You probably don't really care about this too much on the client side, but on the server side, this is definitely huge. Also, last but not least, reftables will actually become the default in Git 3.0. So if you use Git in your scripts, or if you use Git on the server side, then you should definitely verify that you don't play any weird games by writing references directly via the file system, for example. You should always access references via Git commands, and if you do so, you shouldn't, in the best case, observe any differences. So thanks a lot for your time, thanks a lot for your attention. Do you have any questions?
Yay!
Are you actually working on the GitOxide implementation, or are you trying to get somebody to work on the GitOxide implementation?
So the question is whether I'm going to work on GitOxide myself or whether I will just like force somebody else to do it. I will, like the mode that I'm aiming for is like basically a split where I will probably sit together with Sebastian Thiel where he teaches me a little bit of Rust, I teach him a little bit of reftable, and then I will hopefully implement reftable myself, but no promise there. Coffee is probably also ready. But yeah, I do plan to work on it myself, but it will definitely take a while. And if somebody else wants to help out, I'm very game.
You said Crates is libgit 2-based. For some reason, I thought it was GitOxide based. Are they using both?
I think GitOxide just isn't mature enough for stuff that Crates want to use.
Oh, okay.
Yeah.
I thought that it was doing.
It could also be moving by now. I know that originally it had like Cargo has been implemented on top of libgit 2. It could be that it's changing, but I don't really know enough about the current state. Yeah.
Yeah. They use it for certain things, so I just don't know about this particular operation. If they use libgit 2 or
We are aware.
Any more questions? Chris?
I just wanted to say that it might be possible to use the reftable format in the Git protocol
Yeah. Like there is an existing idea from Chris where you can basically say that it's possible to, like whenever you fetch, for example, from a remote, the remote has to always announce like all the available references. Chris had the idea that we can like basically also optimize that to use reftables in that protocol, so that we also have to basically transmit way less data over the wire, because eventually, like I've seen repositories where you actually have to like download 100 megabytes of references only to upload a single object, which is kind of stupid.